Okay, so now we will look at some of the questions which I think are important for your upcoming quizzes and exams. Um, so distinguish between active attacks and passive attacks. We have that in the material. So active attack is something that causes harm to a victim, whereas a passive attack is something that does not cause harm. People just try to extract information from what they see. So active attacks mainly focus on detection. For example, you could have a firewall or intrusion detection system to detect traffic, malicious traffic getting into your network, and we try to recover from the effects of an attack. That's the focus on active attacks. Whereas in passive attacks, we try to kind of prevent them from happening. So if someone could capture your traffic and analyze the contents, then we'll try to make it difficult for them to do it or kind of prevent it by using schemes like encryption. Okay, so here I'm going to give you only small hint kind of information. So it's up to you to get all the detailed answer. Okay, so I'm not going to go over the entire thing again. Now distinguish between a security mechanism and security service. So security mechanism is first of all, security service is something that we provide to the users or the end users, or sometimes the organization employs certain services to maintain the secrecy of the data and information. So the services are mainly intended to counter the security attacks, and how these services are provided by making use of one or more security mechanisms. Okay, so example for a service could be authentication or access control or confidentiality of your data, integrity, non-repudiation, availability. So all these are examples of services. How these services are provided by using one or more security mechanisms. So a mechanism is mainly something that is designed to detect, prevent, or recover from a security attack, in the sense that they kind of help us to implement one or more of the services. So for example, if we can achieve data confidentiality by encrypting the data. So data confidentiality is a service, whereas encryption is a mechanism that helps us to obtain that service or provide that service. And similarly, data integrity is a service, and we can make use of the schemes like digital signature as well as encryption to obtain data integrity. Okay, so you could explain things like that using examples. All right, then the definitions of these terminologies are already there. Um, okay, data confidentiality, privacy, data integrity, system integrity, availability, authentication, both user and message authentication, accountability, and so on. So just refer to them, they are out there. Okay, as well as the terminologies for this vulnerability, threat, and everything. Okay, so they are here too. All right. Then module 2, the three classes of public key certificates and when and how they are used. So what are the three classes? Class, we call it ABC or 1, 2, 3? Okay, so let me see here. Okay, class 1, 2, 3. So class 1 is kind of for individual users. So if I want to digitally sign my email, I can use a class 1 certificate. Class 2 certificate is mainly for software signing. So if you want to distribute your software over the internet, you better sign it with a class 2 certificate that you obtain from a valid certifying authority. Now class 3 is more called a CA certificate, in the sense that class 1 and 2 are called end entity certificates because they're used by individual users or whoever is developing a software and distributing them. Whereas a class 3 certificate can be used to issue certificates for other entities. Okay, so if you are running an organization, you don't require your individual users to obtain their class 1 and 2 certificates from a well-known certifying authority outside your network. You can obtain a class 3 certificate from that well-known certifying authority. Then you can indirectly provide these end entities their certificates. Okay, so this way you are kind of reducing overhead associated with each end entity in your organization contacting the outside certifying authority. Okay. So what are the different approaches for key distribution that we did in this course? We did the Needham-Schroeder protocol. We did also this use of public key authority, right? So Needham-Schroeder, and then using a public key authority to distribute the public keys of the end users itself, and then once they get each other's public key, we can then send a secret key. Then this Diffie-Hellman key exchange algorithm. Um, you could use PGP also, because PGP, if you want to use for distributing a key that you generated randomly at the time of sending the message, then we can use PGP for authentication and confidentiality. Okay, so these are like 4 different mechanisms that we have seen for key distribution. So we briefly explained them. Now explain the use of a nonce for remote user authentication. Okay. Uh, so a nonce is basically used to make sure the other person has the secret key. So what we do is we generate a random number, right, and encrypt that random number. So let's say random number is some number n. So we encrypt this n with the secret key and send it to the other side. The other side need to have the right key to decrypt it, and then increment it, and then send the incremented number in an encrypted form, encrypted with the secret key, the same secret key. So when we receive it, we decrypt it, and if we see an incremented version of the random number, then we are sure that the other side was able to decrypt that random number with the appropriate secret key, and then only they could have incremented it and sent it back. Because the random numbers are typically generated from a huge range, from 0 to 2 to the power, say 128 minus 1. So it's a huge range of for the random numbers. So it's kind of going to be very difficult, almost impossible, for an attacker to guess a random number for that particular time instant and send it instead of the receiver doing it. Also, they have to use the right key, the secret key, to, even if they generate the same random number, they have to use the right secret key to encrypt it and send it. All right. And also, the reason why we need to increment the random number instead of just sending it back is to avoid replay attacks, because we don't want an attacker to capture the random number and send it right as it is. So that could generate replay attacks. They could make the reply to come from the valid receiver by using IP spoofing. So we do not want an attacker to do that. So that's why it's very important that we increment this random number instead of just sending the same number. So that only the appropriate receiver with the right secret key could do it. Okay. Now, how PGP provides authentication, confidentiality, and authentication together, so individually. So how it just provides authentication means we want to make sure it comes from the right sender. So you have the message, and then the hash value of the message encrypted with the private key of the sender, and you put these two things together and compress it. So when you send it, the receiver has to decrypt this with the public key of the sender and compute the hash value of the message from this side and compare the two hash values. Now, if how do you authenticate that it came from the sender is, if somebody else wanted to send it, they could generate this message and its hash value, but they cannot encrypt that with the private key of the sender. Only the sender knows its private key. So if they encrypt it with some other private key, then if you think that the message came from the particular sender, so when you decrypt it and compare the two hash values, they won't match. So this way, when you encrypt the hash value of the message with the private key of the sender, you could provide authentication as well as integrity, because if someone again changed the message during transmission, they could not again encrypt the hash value of that message with the private key of the sender. So when you do like this, okay, so the key thing is to encrypt, the important thing is to encrypt the hash value of the message with the private key of the sender. This way you are providing both authentication and integrity simultaneously. Now, how to provide confidentiality alone? just send the message, right? But encrypt the message with a randomly generated secret key. And so the receiver will not even know the secret key. So since the receiver will not know the secret key to start with, you have to send the secret key along with your message. So encrypt the message with a randomly generated secret key, and then send the secret key along with the message by encrypting the secret key with the public key of the receiver, so that only the receiver can decrypt with its private key. So the receiver gets it, it has to first decrypt this portion, extract the secret key from using the private key of the receiver, and then use that secret key to decrypt this portion and extract the message. Then how to provide both confidentiality and authentication that goes along with integrity is put these two things together. So you have the message and its hash value encrypted with the private key of the sender. Now we want confidentiality, so we encrypt the whole thing, of course the compressed version of this whole thing, with the randomly generated secret key, and send the secret key in this encrypted form along by encrypting that with the public key of the receiver. Okay, so when the receiver gets it, it has to decrypt this portion to extract the secret key. So it will decrypt using its private key, and then go to here to decrypt this portion, extract the message, and then decrypt this portion using the public key of the sender, extract the hash value, and then compute the hash value of this message and see if the two hash values match. So this way you can provide all the three together: confidentiality because of the encrypting the secret key, and sending that with the private key of the with the encrypted the public key of the receiver, and then integrity and authentication because of encrypting the hash value of the message with the private key of the sender. Okay. So explain the following properties of a hash function. You have these three properties. One-way property means you can find the hash value of a given message by just running the message, passing the message to a hashing algorithm. But given the hash value, it would not be possible for us to find out the original message. Okay. Then there are two things: weak collision resistant and strong collision resistant. So what are they? So a weak collision resistant means for a particular message, right, we should not be able to find very easily another message that has the same hash value. Whereas strong collision resistant means we should not be able to find any two messages, okay, that have the same hash value when we go through the particular hashing algorithm. So these two properties, or even all the three: one-way property, weak collision resistant, strong collision resistant, are all the properties of the hashing algorithms. Okay. So for any given message, if you are not able to find another message of the same hash value that easily, then the algorithm is said to be weak collision resistant. Then we cannot find for any message pairs, any two message pairs that have the same hash value, then that is even more preferable. Then it's called a strong collision resistant property. Okay. All right, then man in the middle attack and the cryptographic solution for it, we saw that. So you have Alice trying to send something to Bob. Okay, so Alice and Bob are communicating, and initially Alice does not have the public key of Bob. So Alice asks Bob to send his public key. So Bob sends his public key to Alice, but Mallory intercepts it. So Mallory has the public key of Bob. Okay, so Mallory has the public key of Bob. So when when Alice sends the actual message, right, Mallory intercepts the actual message. So actually what Mallory does is Mallory has a public key of Bob and sends Alice sends Mallory's public key, her own public key, to Alice. So what Alice gets is Mallory's public key, but Alice thinks that she's basically getting Bob's public key. Okay. So when Alice sends a message, Alice encrypts the message with Mallory's, thinking that she's encrypting with Bob's public key, but actually she's encrypting the message with Mallory's public key. So Mallory could decrypt that message with her private key and change its contents if needed, or at least find out what is there, and then encrypt with the public key of Bob. So only when Bob gets it, he can only decrypt with his private key, but already the damage is done because Mallory was able to change the message. Okay. So the problem occurred because of Bob sending his public key, okay, as it is on the channel, and Mallory was able to grab it and send her own public key to Alice and make her believe that whatever she's getting is the public key of Bob. So how to prevent that is to use public key certificates. A public key certificate is an encrypted version of your public key. It is encrypted using the private key of the certifying authority. So if you let Bob to send his public key certificate instead of the public key, even though Mallory can get it and decrypt the public key certificate with the public key of the certifying authority and learn about the public key of Bob, she cannot send her public key to Alice, because when Alice gets, she's expecting a public key certificate now, right? So a public key certificate is again what? The public key of the user encrypted with the private key of the certifying authority. So when Alice gets, say, Mallory's public key certificate, she decrypts it with the public key of the certifying authority and sees it as Mallory's public key certificate, because remember the public key certificate also has what? The user ID, name, and all these things, and also the hash value of the public keys. So Mallory cannot forge all these things and sign that with the private key or the certifying authority. So nobody can forge the public key certificate for a user. Only the public key certificate, the certifying authority can sign the public key of the user and generate the public key certificate. Okay. So this one, so assume the sender randomly generated a message and you want to send and you want to encrypt the message with the secret key, right? The secret key was randomly generated and the sender wanted to send the message encrypted with the newly or randomly generated secret key. So the receiver has to know the secret key, right? So you send the secret key along with the encrypted message. So it's nothing but basically PGP with all these three properties. We want PGP to provide confidentiality, integrity, and authentication. Okay.